Today we'll take an introductory look at DSP technology, functions, applications, and where we will find this technology. We'll take a look at what role DSP plays in our audio products and why these features are important to us, how it is applied, and when do we use it. In closing, we'll take a brief look at some of the TOA products that have DSP capabilities. The term DSP stands for Digital Signal Processing. It is a process of turning anything analog into a digital format, expressed as a binary number of zeros and ones. Many of today's audio products use this conversion technique by applying an analog to digital converter, or ADC. Once the signal is in the digital domain, it will allow the device to shape and control this signal, often with the use of microprocessors. This level of control enables many sophisticated processes as well as simple process similar to what we can do in the analog domain. After processing, the digital representation of this analog signal is then converted back to the analog world by using a digital to analog converter called a DAC. Here is an example of an analog signal, in this case a pure sine wave with a specific frequency and signal level measured in volts. This signal has an infinite voltage resolution, only limited by the apparatus that we use to measure it. When the analog signal is processed by the ADC, it is sampled or sliced up into individual segments. These segments are defined by the sample frequency, and some popular rates are 44.1 to 192 kilohertz. This sampling frequency should always be at a minimum of twice the highest expected frequency of the analog signal. At each individual sample, the ADC will assign a numeric value based on the signal strength of the signal at a particular instance in time. This numeric value will be based on the word side expressed in bits. As an example, an 8-bit word can express a discrete number of 256 levels. Larger word bits of 16 and 24 have a much finer representation. It is desirable to have a word length as high as possible, and is more critical in the final processing than a higher sample rate. Once the analog signal is converted, we will now get a digital representation of the analog version. As you can see, the digital signal has many discrete steps, and increasing the sample rate and word length can help reduce this coarse stepping, leading to a more faithful reproduction. Here we see the numeric equivalent expressed as a decimal number. Since this is an 8-bit word sample, the numbers will vary between 0 and 255 for a total of 256 data points. What the microprocessor sees and understands is really in a binary format, and in this case we have an 8-bit word. A representation of the decimal numbers in binary zeros and ones of 8 bits long is shown. Same information, just a different numbering system. So what does this process look like in a typical audio product? On the left we see the analog signal entering the ADC. The conversion is then applied as described above. Once digitized, specific processes can now be affected by the microprocessor or by manual control by the operator. After processing, the results are then converted back to the analog domain for further processing by the amplifiers and then delivery to the speakers. Now that we have looked at getting our analog signal into the digital domain, where would we find such processes? DSP technology has been commercially available to the audio world since the early 1980s. In fact, TOA Corporation was the first to bring to market such a device called the Hysteresis. However, in today's world, DSP is not relegated only to the audio world. We find it in most everyday appliances around us. This technology has allowed manufacturers to decrease the size of products and manipulate signals in a highly sophisticated way that many years ago were just not possible. With this decrease in size, manufacturers can now deliver many separate functions that took multiple devices and place them in a single, smaller product. As you can see, there are approximately 8 devices from the left contained in any one of the products on the right. For audio, we find DSP mixers with filter capabilities, matrix patch bays, and speaker processors to ambient noise compensation. Now that we know how the digital signal is made and where we find it, what can the audio technician use DSP for? When to use it, and why are these desirable features? DSP technology comes at a cost. The single unit pricing is higher than any one of the single devices that would be part of the makeup of the full-featured DSP product. We would not likely use a DSP product for simple background music because of cost, unless it was one of our multi-purpose units like the TOA 9000 M2, where the full-featured technology is best leverage would be for a large multi-speaker installation, complex routing of signals using the matrix feature, and possibly performance-based installations such as theaters and house of worship, to name a few. Some of the basic functions similar to analog processing would be tone control, parametric equalization, signal control using compression and leveling, etc. Some additional, more complex functions taking advantage of microprocessor control would be auto mixing, feedback control, automated room tuning, and ambient noise compensation. As mentioned before, a single DSP product will cost more than a single analog device. However, the functionality is more extensive than the single analog unit. So care must be exercised on when to use these products to make sure that the cost is warranted. Some advantages when comparing the equivalent functionality to analog products would be the increase of signal to noise, since reduced cabling and signal paths are eliminated, ease of installation with seamless integration between various components, less input and output signal manipulation as the signal is contained in one product, reductions of labor as cabling and rack space are reduced, the possibility to control and automate various functions using third-party controllers, and programming by computer allows one to see the complete functionality and the saving of the setting files for backup. Also, improved performance or new features can be implemented without changing hardware with a firmware or software update. Now that we have looked at DSP as a function, product, and appliance, let's look at the various components of DSP, such as the software signal path and various functions that make the process useful. Here is a typical software configuration page using the TOA D901. The layout is very straightforward, so I'll be using it to show the various functions that are accomplished in a typical product. Different products will have software that may look different, but actually accomplish and operate much in the same way. On the left is the analog input, ready to receive the input. With the input applied to the ADC, the signal is now in the digital domain where the processing can begin. Once processed, the signal emerges from the right and is converted using the DAC back to the analog signal. Looking just inside the digital section, we can see the various processes that are available. The filtering of inputs and outputs, level control, and a method to steer the input signal to the appropriate output via the matrix are all done here. Here's a screenshot of the TOA M864D. Looks different, but has similar arrangement. Another software version showing the TOA D2008 SP. Again, looks different, but basically accomplishes the same thing. These products will have the same basic functions of filtering, but may employ more control or advanced features allowed by microprocessor control. Let's look at the terminology used to describe the various attributes defining the various functions. For filtering, the term corner frequency defines the frequency point at which a filter begins to change towards the desired slope. This can be a reduction or increase in gain. In this case, 500 Hz is the corner frequency, and the filter will begin to have reduction in gain to lower signal levels. The slope is the area that is most linear, indicated by the brackets. In this case, the reduction is 6 dB per octave as selected in the software and produces a gradual change. We can see in this example, the corner frequency stays the same, but the filter slope has been set to 12 dB per octave, a much steeper curve. Certain filters allow us to control the sharpness or width of the filter around the selected center frequency. This is defined as Q, or quality factor. In this example, the center frequency is 1000 Hz with a Q of 1.011. Signals inside of this filter are passed, unattenuated at the center frequency, and gradually attenuated as defined by the Q width. A smaller Q number creates a wider filter, and a larger number a sharper curve or narrower filter. This example shows a wide bandwidth filter. Here we see a smaller Q, and as such, the filter is now narrower, rejecting more frequencies outside of the filter passband. How is Q determined or defined? Basically, it is the -3 dB point on either side of the center frequency. Mathematically, these 2 points, the lower and upper frequency at the 3 dB down point, are subtracted and divided into the center frequency, thus providing width or Q of the filter. But no need to deal with the math. The TOA products provide a pull-down menu that allows one to pick possible Q settings. Once selected, the results are available for viewing in the graphical representation. Now that we have some of the terminology understood, let's now look at the specific filters that apply this terminology and where they are located in a typical signal path. The high-low pass and the PEQ filters are available at the inputs and outputs. The first ones we'll look at are the high-pass and low-pass filters. The high-pass filters will pass high frequencies as set by the corner frequency and the amount of attenuation to lower frequency determined by the slope. In this case, 100 Hz for the corner frequency and a 12 dB per octave slope. This filter is useful to help reduce low-frequency muddiness, circuit hum, and to remove signals that are not expected from the device connected. As an example, there is no need to pass frequencies below 200 Hz for the human voice, and it seldom is capable of reaching these low frequencies when speaking. We can also adjust the Q of the filter to provide some gain at the corner frequency. Depending on the Q selected, this can impart a signal boost or even increase the slope of the defined curve. Like the high-pass filter, the low-pass filter has all the same capabilities except that it passes the lower frequency and rejects the higher ones. Helpful for controlling high-frequency brightness, circuit hiss, and again rejecting frequencies not expected from the sending device. These two filters act like variable tone controls that lower the gain of frequencies outside of the pass band. A special type of high and low pass filters are used to develop crossovers that we will discuss later. What happens when we put both filters together? Here's an example of combining the two filters, creating a band pass that is defined by the two corner frequencies. This filter would pass frequencies at unity between approximately 200 and 8,000 Hz. Another class of filter is the PEQ, or parametric equalizer filter. With this filter, we can adjust the gain at the center frequency, control the width by adjusting the Q, and position the center frequency higher and lower. As compared to the typical graphic equalizer, which has fixed center frequencies and fixed Qs, the PEQ is suitable for precise tonal control, removing system resonances caused by room geometry, controlling feedback by notching out offending frequencies, and providing sonic impact. Later, we will see that the PEQ can be used by manufacturers to enhance speaker performance. Here are some examples of a PEQ filter with different Qs, gain, and center frequencies. When multiple PEQs are used, complex filter arrangements can be achieved. High and low shelving are basically tone controls for the low and high frequencies. Their corner frequencies and gain are adjustable. These can be added together as illustrated here. The notch filter provides a very narrow fixed cut or gain reduction around its center frequency. They have very high Q widths. These filters are often used for eliminating feedback, specific unwanted frequencies such as 60-cycle hum, lighting dimmer noise, or any narrow unwanted signal. Let's now look at the specific purpose filter used, such as speaker crossovers and speaker frequency shaping, often referred to as speaker PEQs. The crossover will steer the appropriate frequencies to the correct speaker, while the speaker PEQs will provide the best frequency response by the speaker system. We will use the TOA HX5 full-range speaker and the FB120 low-frequency speaker to demonstrate the crossover configuration. This is a two-way crossover, but it is possible to build out a 3- and 4-way version. When setting up the crossover, the speaker manufacturer should be able to supply the correct parameters required to set the crossover and the specific filtering for the speakers. This is not guesswork, so you must obtain these parameters first. A typical table would look like the chart provided here. First, the crossover. The low-frequency speaker will require the low-pass filter with a specific filter slope and corner frequency. The high-frequency speaker will require the high-pass filter and a specific slope and corner frequency. Once the low pass, which is in green, and the high pass, which is in blue, filters are set, the possible total results of the combined two speaker groups is shown in red. This is the possible total frequencies that could be passed by the filter set. Keep in mind that speakers will not be able to pass such a wide range and will have natural attenuation at the low and high frequencies. Addition of speaker filtering will also address the lows and the highs, as we will see in the next step. Any irregularities, such as the bump seen here at the crossover by the red line, can be compensated for later by applying the speaker PEQs. We can now add in specific filters to make the speakers perform at their best. Again, these parameters are provided by the speaker manufacturer. Here we have added the necessary high-pass filter for the low-frequency FB120 and the PEQs for the full-range HX5. The combined response with the crossover and speaker PEQs will now look like this for the two speaker types. With this filter management, the speakers will perform their best and be protected from frequencies that they would not normally be expected to pass. A much smoother response is possible. There are times when multiple speaker groups are separated in space because we are trying to cover large areas. An example of this might be an arena where the center ice and the seating must be covered, but by different speaker systems. Another example would be in a house of worship or theater when we have speakers at the front and speakers further back in the audience. Since the sound coming from the front speakers will arrive later than the speakers closer to the audience, covered by the rear speakers, the wave fronts will arrive at different times. This can lead to hearing fatigue, discrete echoes being heard, and loss of intelligibility. To correct for this, we must delay the rear speakers so that the sound coming from these speakers arrives at the same time as the sound coming from the front speakers. To do this may require several delayed channels feeding individual power amplifiers, with the delay at the output of the DSP channels feeding the delayed speakers. Speaker management could also use micro delay during the setup of the crossovers should the different speakers not be aligned on the same acoustic centers. This is being illustrated by the dotted speaker outline. This speaker is now acoustically aligned with the low frequency speaker by adding a small amount of delay. We are finished with our discussion of filters and now move on to another class of DSP used to manage signals at the input and output. Compressors have the ability to attenuate signal based on the signal level and at what point we would want the signal to start this attenuation. The compressor will pass a signal in a linear fashion unaltered until the set threshold is reached. At this point, the gain is reduced at a fixed amount until the maximum allowable level is reached. In this example, the signal will not be affected until minus 10 dB is reached. At that point, the gain will be reduced for increasing signal strength at the value set by a ratio, in this case on a 3-to-1 basis. The signal must increase by a factor of 3 to produce an output of 1. Compression protects the input signal chain from damaging clipping and speaker damage on the output by controlling the maximum signal to the speakers. Other parameters control how quickly the compressor responds to the changes as signal increases and decreases. Levelers will try to maintain a window of signal level determined by values set as the target, minus 20 dB in this case, and maximum gain, which is 20 dB, as illustrated here. As can be seen from the graph, up until the target level is reached, added gain is applied to signals that are lower than this set value of minus 20 dB. The red circle shows one data point. You can see that the input level, if minus 60 dB, will produce an output level of minus 40 dB. This is useful for BGM sources that have a wide dynamic volume range, and when used carefully for mic inputs to make sure that the page is always within a certain volume level. AutoMix features provide operatorless gain control for multiple microphones in a system. Microphones are turned on and off as needed based on the trigger value set by the gate threshold. With the NOM selected for microphones included into the group, as a number of mics are doubled, for example from 2 to 4, the system gain is reduced by the equation 20 log NOM. Standard NOM value of 20 provides 6 dB of attenuation for doubling of microphones, but other values for NOM may be used with less aggressive gain reduction. Having auto mix allows a system to manage gain as microphones are added and removed, thus eliminating the need to have an operator ride the gain of the system to prevent the system going into feedback. The gate hysteresis helps smooth out when the switching occurs at the turn on and turn off point. They will occur at different times, thus reducing any switching artifacts. The matrix. As the name applies, the matrix provides a connection point to route inputs to outputs. Multiple inputs can be routed to the same output or different outputs depending on the requirements. At each relationship to input and output, called a cross point, the volume level may be adjusted. This will allow a single source to be routed to different outputs at different audio levels. Under scene control, many scenarios can be accomplished as to what inputs are required to certain outputs as the need dictates. ARC and FBF are specialized processes that are possible with microprocessor-controlled DSP. These functions cannot be done without the digital process under microprocessor control. ARC is a TOA Corporation proprietary process. It stands for Acoustic Resonance Control. By sending different built-in test signals through the speaker system, the room resonance and speaker placement are analyzed. After analysis, filters are placed into the system to help reduce room mode artifacts that show up as hotspots. This process will improve overall system stability and increase in system gain with the benefit of increasing speech intelligibility. It's as simple as placing a microphone or microphones in the room and pressing a single button. Feedback suppression automatically applies a set of notch filters in the system to help reduce the chance of feedback. There are two types of filters available, dynamic and static, depending on the product. Static filters are set and remain fixed as a general filter for reducing the hot spots in a room. Dynamic filters are always added and removed depending on the requirements at any given instance in time. With these two features of ARC and FBS, almost any acoustically challenging room can be tamed. A very specialized form of DSP process is now embedded in the TOA SRDA steerable line array. Due to the miniaturization, microprocessor control, and rich DSP functions, line arrays such as the TOA SRDA can produce steerable and width-adjustable audio beams to direct sound where you need it. Not only do you benefit from line array technology, having these features allows mounting the speakers flat to the wall and covering different audience areas by steering the beam. With scene memory, different configurations depending on the seating can be set up without having to move the speakers. We will now take a quick look at TOA products employing DSP technology. From our entry-level 9000 M2 digital mixer amplifier to the high-end D2008 SP digital speaker processor, TOA has most scenarios covered. Dedicated ambient noise compensation products, another form of DSP to adjust gain associated with changing environmental ambient noise, is also available for the 9000 M2 and as the DPL2. We can also find DSP in our network-based intercom to our voice evacuation SX system. In conclusion, we can leverage the power of DSP depending on the application and budget required by the system. Place these products where suitable and where the cost is warranted. Some analog solutions may be appropriate depending on the application, so choose wisely. TOA Canada can help with any of the software setups by programming and emailing the setting files. Training is also available for these products on request. Some things to keep in mind: don't overuse filters. Try to get the best performance with speaker selection and placement. Don't boost filter gain to high levels, as this may lead to exaggerated power requirements for the speakers. Use filters to reduce gain in some troublesome frequencies and boost overall gain to compensate for signal loss when using these filters. DSP has a finite signal level bandwidth as defined by the word size. Use as much of it as possible without saturating or clipping the signal. Input should be driven to strong levels without clipping and maintained throughout the digital domain. The final volume level should be adjusted at the amplifier. On a closing note, when using any computer-based product, please always make sure you have the latest firmware and software for the product. Updates may enhance and improve the product. Thank you for attending today's webinar, and I hope you have a better understanding of DSP functions and terminology.